Today, starting us off with our Open Chemical Sciences week, we have Jan, who's going to talk a bit about using UsingGoogleCoLab for doing quantum chemistry. And I'll now make him the presenter. Okay, over to you.
Right. Thank you very much. Okay, that's the wrong. Let's see. Are you seeing a? Yeah, you're seeing my screen now, I think, right?
Yeah, yeah.
Okay, so I guess the first thing I should check with everyone is whether the font is big enough to read. Or should I try to make it bigger?
That seems fine to me.
Okay, let me know if someone in the chat complains. Okay, so hello and welcome. My name is Jan Jensen. I'm a computational chemist at the University of Copenhagen. And I want to show you a little bit about how to do quantum chemistry on UsingGoogleCoLab. Actually, so when Chris and I originally got this idea, my thinking was sort of that it would be interesting for two different groups of people. So one would be people who are more in the cheminformatics business, so who's used to dealing with thousands of molecules, and maybe they would want to have access to some quantum information, for example, from machine learning and things like that. So people who are familiar with cheminformatics, and for many people it means to be familiar with the RD-Kit tools, who would like to learn some quantum chemistry or to interface with some of those programs. And then the other group would be people who are used to running quantum chemical calculations, but perhaps are doing it more by hand and would be interested in learning how to automate things. And so I realized that sort of the title that we came up with very many months ago doesn't really capture this, but that's basically the idea. So I chose UsingGoogleCoLab because it's a very useful sort of tool for not having any installation and such, but what I'm going to tell you is completely general and does not really ultimately depend on UsingGoogleCoLab. But let me just, many of you filled out this form. I just want to sort of show you where we ended up. So I had this 4-question questionnaire. How familiar are you with Python? 1 being unfamiliar and 5 being very familiar. So our group here are basically people who are familiar with Python, not at all familiar with UsingGoogleCoLab, and not very familiar with RD-Kit. And finally, quite familiar with running quantum calculations. So it seems like it was mostly the second group. So quantum chemists who would like to know something about maybe automating these quantum calculations, sort of doing it in a different way. So that's but I realize it is mixed with sort of many degrees of being comfortable with one or the other. So if there are questions along the way, please ask them. I believe you ask them in the questions window. Chris, do you want to say something about that, how people can ask questions?
So if they ask questions in the questions window, I'll monitor that window and then I can relay them to you at suitable points in the presentation.
Okay, yeah, feel free to do that. Okay, so I should say a little bit about UsingGoogleCoLab. So UsingGoogleCoLab is an online Jupyter notebook. So for those of you who aren't familiar with notebooks, you'll see how this works. So basically, UsingGoogleCoLab works the same as a normal Jupyter notebook, if you're familiar with that. The main difference is that it's running on a virtual machine that's supplied by Google. And this virtual machine sort of is assigned on a session-to-session basis. So the advantages, I'll come to the advantages of Google Colab, but sort of the one disadvantage is that if you leave a session for more than a few hours and you want to start working on it again, you have to reinstall everything and upload all the data files that you're using. But as I'll show you, doing that is actually quite simple. The advantages of Google Colab is many. I use this especially for teaching. So the only thing you really need is a web browser, and all the installation can basically be pre-configured like I've done in this notebook here. And so you get access to a dual use CPU. You can also get access to GPUs if you're doing any machine learning, and you can access that here by changing the runtime. That's under tools, I think. Change runtime is under here. So you can switch to GPU and TPU. That's only really useful if the software you're using can take advantage of this. But so if you're doing any machine learning, that's a good feature to have. And I should say that all the major machine learning code, like TensorFlow and PyTorch and things like that, are already pre-installed on Google Colab. So this is not something you have to install yourself. So the advantage is that you can, there's no installation, and it's very easy to share your notebook with other people. Like I have shared this notebook here with you. To do that, you just go up here under Share, and then you can change permissions who are allowed to see it and that, and you can basically copy a link and share it with people. So you can either do it publicly, or you can invite certain people to work with the notebook together with you on the notebook, and so that's also incredibly useful. So it's a little bit like Google Word, Google Docs, or Google Sheets, but it's just for programming instead, for Python and Jupyter notebooks. So like I say, I use it a lot.
Jan,
Yes?
would it be possible to make that a bit full screen, or just expand it a little bit?
Yes.
Use as much
like
real
this?
estate as possible. Yeah, that'd be good.
Okay.
Great, thanks.
Sure. Yeah, so I use it for teaching, and actually I use it for all sorts of prototyping of code. Another nice feature is once you have everything written, you can also download this either as a notebook or as raw Python, and so you can do that with this notebook as well. Okay, so that's basically my introduction to Google Colab. So there's nothing really special about it from one point of view, but except that it's very easy to share with other people, and so I thought it was perfect for this kind of thing where you don't have to install anything on your own computer, but you can obviously reproduce this environment on your own computer if you find any of this useful. Okay, so let's actually get started. So to start, you should all have gotten a link to this site here, and so you can in this workshop you can basically do one of two things. So you can follow along. So I'll do some live coding, which is always dangerous, but I hope it goes well, and you're welcome to follow along. Or you can sort of sit back and relax a little and just watch what's going on. I believe this session is being recorded, so you can always come back and if you want to reproduce what I'm doing later, when perhaps in a little more stressless environment.
Yeah, that's correct. We're recording it, and we'll send out the link to everybody who's registered.
Yeah, great. And also this notebook. So I will sort of live code in this notebook. So you have the link to this notebook now. You can always come back, and the code I'm writing will sort of appear there. But if you do want to follow along, you can't write in this notebook because I haven't given you permission. So what you have to do if you want to follow along is click here on Save a Copy and Drive. So you go to File and Save a Copy and Drive, and it'll then open up a new copy of the notebook. So it's taking a little longer because I also have this GoToWebinar running, so that's eating a little bit of the memory and CPU. Normally this is quite fast. Okay, so you should have a copy of this now. If you want to rename it, you can go up here and rename it. You don't have to. And the first thing to do is we're going to install some things here. And that's going to take about 2 or 3 minutes. So if you want to work along with this, it's probably a good idea to start that now. So you can go into Run All, which will run all the cells and start the installation process. So I'll do that here too, just so you can see. So this will run for about 2 or 3 minutes. So while it does that, I can tell you a little bit about some other features of this and what it does. So we're gonna use RDKit, which you'll learn a lot about. It's a cheminformatics toolkit for manipulating molecules. And for our quantum program, we'll use an open source semi-empirical program called XTB. And there's a link here to the documentation. So what we're doing here is we're going to install this on the machine. So you basically have a normal Linux machine. And we're going to install Conda. And once we've installed Conda, we're going to install a version. So RDKit works with Python 7.3. Then we're going to install RDKit. Then we're going to install XTB, the XTB program. And then we're going to install a program called Py3Demo, which is a way of visualizing molecules. And so what you can see here is basically that you have...
Just a sec. I've to everybody, I've got a few questions about getting access to the notebook, so I've put the link in the chat box. So if anybody's missing it, they can get it there.
Super.
Great.
Chris, I think it may have, does it have to go in the questions box rather than the chat? The response? I'm not sure. I'm not sure if everybody can see the chat. They probably can.
So I can see it for whatever it's worth. And it says to all. So
sorry, my bad, my mistake.
Okay. Okay, over to you.
Yeah, okay. So you have in the notebook, you have coding cells and text cells. So this is a text cell, this is a coding cell. And in the coding cell, you can write Python, but you can also write any bash command that you would want. So conda, things like conda, wget for getting files, and pip, things like that. If you're used to Linux, all work on the notebook. So I can see mine is finished. So you can, yeah, I guess the easiest way to tell is simply to look up here. So when this goes from gray to orange again, then you've done the installation and you've run through all the subroutines that I have. So you can see the sort of the outline of the notebook that you have here out on the left-hand side. So I can, to get it, you go, I believe it's here for outline, and then you can sort of turn it off again here. And this shows you an outline, so the installation and imports. There are some functions that we're going to use, and then here is sort of the actual, this is where the actual chemistry happens, where the actual coding happens down here. So before we go down there, I just want to mention these two things here. So basically what I'm going to take you through is basically a way of making RDKit talk to the XTB quantum program. Now I chose XTB because it's open source and it's very fast, so it's good for a workshop like this. But I also want to give you sort of ideas on how you can interface this with anything else, like Gaussian or games or any other quantum program. So I'll sort of give you ideas on how to do that. There are a couple of packages that have already done this for some programs that I encourage you to look at. So scikit, which is an interface to the Sci4 quantum package, and ASE, which has an interface to all sorts of programs. And they both have quite good documentation. So basically a lot of the stuff I'm doing here, these packages already do. But I basically wanted to show you it from the ground up so that if your favorite program is not included in these toolkits here, you could actually write the interface yourself. It's actually not that hard. It's a little tedious, but not that hard. So I'll show you some examples of this.
So we have a couple of questions for you.
Yes, please.
One of them is, where are the files installed? Are they on the local computer?
That is it. Thank you for that question. I forgot. So we have, if you click on the folders icon, you can see the files here. So what we did was we have the miniconda, and then we also installed a couple of things. I guess we'll get to that eventually, but we did some Git clones. And so here you have some Git repositories that we've cloned. I'll get to that in a little while. But here, it's also here where you would upload files from your computer. You can also use wget, for example, if you create a link in Dropbox or something similar. But if you simply want to upload a file, you just click here.
But all these files are on the remote computer, aren't they?
They're on the remote computer, and once the session sort of expires, that'll be wiped again.
Yeah.
So you start with a fresh machine every time. Yeah.
And
So
I guess if you're connecting to Gaussian, you would need your own license, I presume.
Yes. Yeah. So basically, it's your machine. You would have to reinstall Gaussian every time. Yeah. So if for that kind of thing, you probably want to do what I'm doing here, but on your server. So Python will be installed, and you can do yeah. So you'd have to install RDKit on your server and some of the other packages here, and then do it there. Or you could use this to generate all the input files and tar them up and just download the input files to your server. But if you wanna run Gaussian here, you would have to install it like you would on a normal Linux machine.
Okay, that sounds great.
Were there other questions? Okay.
Yeah, go ahead.
Yeah, one thing you can also do is if you can interface this with Google Drive. So if you have files on Google Drive, you can access this quite easily here in the notebook. Problem with that is that will only work for you then. So if you share this notebook with someone else, they will not have access to your Google Drive. What I typically do for files that I need, like data files and things like that, I use wget. So I have a Dropbox folder with stuff I want to get up here, and I just create a link there and use wget to get the files, rather than doing it manually. One final thing is, so I use Conda here because that's the easiest way to install XTB. If you just want to use RDKit, there's a much faster installation process here. It takes 10 seconds or something like that. The Conda install is a little bit slower, but it's also more, it's a more general tool. But yes, so just to finish off the files and things like that. So if you want to just run one bash command, you start with an exclamation mark or a bang. So for example, here you can just do an ls, and here, so these are folders. So for example, yeah, so here you can see what's in the folder. So basically you have a normal file system. that you access through. You don't have a command line, but any bash command here will work. Okay, so that's sort of the intro. So let me know if there are any questions here. I'm going to skip. So I'm going to go over here to the thing you just copied. So you can always come back to this link, and this link will be updated with the code that I'm adding. So if you ever get stuck or find it easier to copy paste, just come back here. And so we're going to go down to the first, so what we have here are some functions that we're eventually going to use. But I thought I would start off sort of with the basics. So how do you do a geometry optimization with this? So I'm going to get rid of this here. I don't need that. And so from a sort of a chem informatics point of view, the easiest or the way to sort of input molecules is through something called SMILES. So if you're not familiar with SMILES, it's something ChemDraw can do very easily. So there's a little video that shows you how to make SMILES. I also have a link here to an online sketcher. So if you click on that link, you'll come over here to a graphical user interface. Looks a little bit like ChemDraw. And so if you draw a molecule here, you'll get the SMILES representation here. So I've worked with this a little while. So for very simple molecules, it's a very easy way, if you know the syntax a little, to input molecules. So we're gonna open a code cell. So if you click at the beginning or the end of any cell in here, you will get the option of adding a code cell or a text cell. And so we need a code cell here. And the first thing we're going to do is we're going to make a molecule from SMILES. And so we're just going to have a simple molecule like butane. So here the SMILES syntax is almost self-explanatory. You only define the heavy atoms, right? So basically you have 4 carbon atoms in a straight chain. And so if you're ever in doubt, right, you can now just type mol here. And to run the cell, you either click here on the play button, or you can see if you mouse over that there's a keyboard shortcut, which is on the Mac at least is the command and enter. So, but if I click here, right here you see just a drawing of the molecule. So now you're working with RDKit, and RDKit has a lot of tools that makes it easy to generate molecules in an automated way. We'll come back to how to do that if you want to get it from a file, coordinate file instead. So I have my molecule. There's no hydrogens. So if I want to do a quantum calculation, that's something I definitely want to do. And so if you run it again, you can now see we've now added the hydrogens. Okay, so, but basically what you've defined so far is just sort of the connectivity. So what is bonded to what? If you actually want to do a calculation, you have to generate the 3D coordinates. And so in RDKit language, that's called to embed. To embed is to generate 3D coordinates. And so it does it like so here. And so now it knows you switched from a 2D to a 3D representation. And so now if you show the molecule, right, you get a 3D structure, right? So it's generated the 3D Cartesian coordinates. Now it'll do this randomly. So here you can see we got a gauge conformation. If I run this again, now I got the trans, and if I run it again, I get the gauche again. There aren't very many possibilities here, but for a more complicated molecule, right, you would sort of randomly generate conformations. So we'll come back to that, what to do about that, how to do a conformer search and things like that. But now we have an actual molecule. In general, I always like to minimize this with a molecular mechanics force field. So that's built into RDKit, the Merck molecular mechanics force field, which is good for organic molecules. And so that's called MM optimized molecules. It just occurred to me that I may have some features turned on, like autocomplete, like you just saw here, that you don't. So if you're not seeing exactly what I'm seeing, you can go to Tools here, Settings, and for example, here are automatically triggering code completions and things like that. So this is basically the options that I have turned on. So if you see something that's happening for me, but not for you, then you can change that here. Okay, but to optimize the molecule, you then give it the, I'm going to keep referring to this as the mole object. That's sort of an RDKit sort of lingo, but it's sort of it's an object that carries, a Python object that carries all the information that you've computed about your molecule. So in this case, for example, the 3D coordinates. Now that's going to look very similar, a molecular mechanics optimization. There was already a very good guess. This will just sort of fine tune a few things, but it can save you a bit of time in your quantum calculations. And when you're doing more complicated molecules, it can actually save you a lot of time. So it's always a good idea to sort of minimize. Okay, so now we have our molecule. And so for the quantum chemists, what you have to sort of imagine now is that this is, or what you hopefully can see is that this is something that can be automated fairly easily. So the generation of input geometries, for example, can be done very, very quickly and in a very sort of controlled fashion using RDKit. I'll give you more examples on how to do this, but this is basically just sort of where we're headed, right? So instead of getting a Gauss view or something like that and drawing your molecules and saving the file, you can do it with RDKit. Of course, yes. So I think that's where I want to leave it. So that's sort of where we're headed. So now we want to run a quantum calculation on this. And so we have to write the input file. So if you're at all familiar with quantum calculations, you know what that means. To those of you who don't, most quantum programs take as input a file with the coordinates and often a bunch of keywords that specify exactly what quantum calculation you want to do. So that's what we're going to do here. And so now we're going to take advantage of one of the subroutines, one of the functions that I defined previously. So we're going to give it the mole object, the molecule will be made, and now we're going to give it the name of the input file. And here I just picked some arbitrary name. So this will write the file. Actually, let's do that. And if we now go here and look at our files, you can see the input file is here in our directory. And now we want to run the program. And so we do this with a normal sort of bash command. We're using the XTB program. We give it, so the way the way XTB works is it wants the input file first, and then here you can specify the kind of calculation you want to run. You can also do it in the file. With XTB, I find it most convenient to define it on the command line. So here we're going to do a geometry optimization. So yeah, so let's just, well, let's see. I think I just want to show you what this program does. So if you ever want to write a different file, we can go up here, and look at the function, right? So basically it writes a standard XYZ file. So the number of atoms, which you can see I compute from my mole object. Then it needs a title, which I basically leave blank. No, I call it title, I guess. So I write the number of atoms, the title, and then I write the symbol, the atomic symbol, and the XYZ coordinate. And so you can see how you can, if you're at all familiar with Python, it's quite trivial to change this into, for example, a function that writes a Gaussian input file or a MolPro input file or something like that. So this is sort of a template you can use. Okay, but let's go back here to geometry optimization. I'll hide this. And so if you run this now, so XDB is a little funny in the sense that it sends the output to the screen, which is convenient here in this sort of workshop, but if you're used to files, you can pipe the output into a file like this. But here we'll just get it on the screen, which is kind of convenient here. And so you can see it's a semi-empirical program. It runs very fast, but it does what a normal sort of quantum program does, right? So it's here's the summary of the geometry, and you get things like the total energy, the gradient norm, and the homolume gap. But you have sort of a standard quantum mechanical output. The one thing that's a little bit different here in XTB is that it writes the optimized geometry out to a separate file. We can actually see that out here, since I have the file window open here. So the optimized geometry is in this particular file. So if I want to show the optimized geometry, there's another program that I wrote called showMol. And like I said, it's in this file here. And so here you can see the optimized geometry. So again, not much, molecular mechanics is quite good for a molecule like this, so not much changes. To show you something that does change, so for those of you who are not that familiar with quantum calculations, one thing you have to be careful of if you start using quantum calculations is that bonds can be made or broken. So I want to show you an example of that here. So instead of butane here, let's just copy this. We're gonna do the glycine sweater iron. So we have an NH3 plus group, a couple of carbons, and then a carbonyl. So again, or a carboxylate actually. Again, if you're not familiar with this syntax, you can, just a sec here. You can use a program like this to sketch it, and you'll get the smiles up here. Okay, so let's uncomment this. Right, so here I get my glycine sweater ion. I get a hydrogen bond here between the ammonium and the carboxylate. Right, I write out the input file again. I use the same name and run XDB again. here. And so again, for those of you who are more in the cheminformatics, right, you can see that this is really quite fast. So it's not at all unfeasible to work with thousands to generate quantum information about thousands of molecules with a program such as XDB. But what I want to show here is if I now show the molecule, what you'll notice, right, is that the proton is transferred from here to here, because by default you're doing this optimization in the gas phase without any solvent, and there the sweater ion isn't stable. But this is something, if you come from a sort of a molecular mechanics world and you want to dip your toe in the quantum world, this is something to remember, that things can change. And so you have to sort of build that into your workflow, a test for whether the molecule you're working with is actually the input molecule and not something else. So what I'm showing here is this is just a function that takes the XYZ coordinates and displays them. So this is not really a mole object anymore. So if you want that, I've included this code here, which you already, so this part here you've already run. And so, oh yeah, so I should, as an aside here, so this is another way of getting software onto your virtual machine. You can clone any Git repository with a simple Git clone. And then this is a program I've written that actually reads the XYZ file and creates a mole object from it again. So let's just uncomment this and run it. So now I have a mole object again, and that means I can do things to this that I can handle this the way I do a normal mole object. So now I can just type, let me open another code cell here. So now I can just type mole instead of show mole. Right, and here we are again. Or I can do things like go back to smiles. So mole 2 smiles. That has the hydrogens, so I can also remove the hydrogens, for example, just like I added them before.
Hi, we have a quick question.
Yes.
What kind of semi-empirical approach is used by XTB?
So it's a density functional tight binding model. So it's a bit like DFTB plus, if you're familiar with that. But it's basically it has some pre-computed with DFT Hamiltonian with some extra terms that it then diagonalizes. And then there are various flavors that differ in how you do the self-consistency problem. So there are some, in the default is GFN2, and so there you have some, basically your Hamiltonian depends on your orbitals, and your orbitals depend on the Hamiltonian, and so you do sort of a normal SCF. But there, yeah, that's the short version of this.
Okay, good.
Yep. Okay, this was sort of a little aside. This is also the way. So if you're a quantum chemist, you probably don't have a long list of smiles that representation of your molecules. You probably have a list of coordinates that you want to do something with. And so if you want to manipulate those molecules using RDKit, you can, if you convert your structure files to XYZ, you can then use this tool to make them into a mole object. You don't have to make them into smiles, but into a mole object that you can then manipulate. In fact, as I'll show you here in the next example. So this is just a handy tool to keep in mind. Okay, so this is sort of the really a really basic operation, a geometry optimization. So the next thing is now so you have the output. Now how do you get stuff out of that? And so here I want to open another code cell. So if we go up here and look at our output file, let's say we want to calculate a relative energy, right? You'll need the total energy, the last one in your geometry optimization. So let's get this out of the file. And so if you're really familiar with Python, this is probably a little boring to you. The reason I sort of go into details here with it is that if you're not that familiar with Python and you get this skill set here, then you can really extract anything from any output file. So I think it's worth spending a little bit of time on it. But for those of you who are very familiar with this, maybe you just want to, I don't know, play around with something else a little bit or take a well-needed break. But so to get the output, if we had written a file like a normal quantum program, we could just read in that file. Like I said, XTB is a little bit different in that it sort of sends it to the screen. And that's convenient because we can, with a little function that's called shell, you can pipe the output directly into a string variable, like we have here. So here you simply, the subroutine basically just takes the command that you want to write on your command line. And then it runs the exact same calculation again, and now it sort of pipes the output directly into the string. So if we just, let me call it output. Right, so it's just one long thing here, but it has the information you need. It's actually not quite, for the experts, you'll see it's not quite a string object. So let's make it a string object. Well, and then, for example, if we just want to look at it again in a more readable way, we can use split, which is a very useful command. So it basically, you have one long string and it basically just splits out the string into separate things. This is probably a little vague. So let's make another string here. So we'll make a string here. And what I want to do is split this up into letters. Right, so everywhere there's a space, I want a split. Right, so now I get a list. I've split this up into separate pieces. So what I'm doing here is I'm splitting it up into separate lines. So this is a carriage return or a line break. Actually, it should just show that here. Yeah, and so here you can basically, there's some weird stuff in here, don't worry about that. But basically we have our output back. And so what you can use this for is basically, we want to get at this number. So I'm gonna split it up into using this expression here. Right, so if I use this expression, I basically get a list with two things in it. Everything that came before total energy and anything that came after total energy. And so if I look at the second, remember Python counts from 0, so this is the second element. right? That actually starts with the energy. So if I take this now and split it again, right now I want to split here. Oops. Let's just write it down. And here I want to now take the first thing in this list, which is my energy. Now this is as a string, not a number. Oops. So I can make this a float. Somehow that got deleted. And now I have my number here. And so I went through this excruciating detail just to sort of give you this general tool. So with this, with split, you can basically get anything out of any text file, any information. I'll show you another trick a little later on. But since we want to work with XTB in this particular case, I've written basically some code that does this. So let's get rid of this. So if let's just sort of summarize. So if I have this molecule, right, if I want to start from a smile, I want to add hydrogens, I want to embed it, I want to optimize it. And all that then you can put into one function. That I call run XTB. So I want to give it the mole object. And I want to give it the option. In this case, I want to optimize. And then I want to get the energy out of the output. There. So everything I sort of went through here in quite big detail, right? I've now sort of encapsulated in these two subroutines that we're going to use from now on. And so you can write other subroutines that runs Gaussian and get something different out of the Gaussian log file. This is just sort of an example of this. Okay, so this was sort of the very basics. Now I want to show you something where maybe a little bit more realistic. So we want to calculate a reaction energy. So products minus reactants. And so I thought a little bit about, so it would be nice to have a reaction energy where we all have, or at least a lot of us have some idea of what to expect. And so pKa's is a good example of this. So if you're not super familiar with pKa's, we have this very handy page here that's made by our panelist. And so these are sort of well-known constants or well-known values that say something about the reaction energy through this relationship here, so through some constant. The problem with calculating pKa's directly is that this is hard to sort of calculate the free energy of a proton in solution. It's also hard to measure quite accurately. So one thing you can do is just calculate a change in pKa relative to some reference molecule. So that's what we're going to do. And here, just for illustrative purposes, we're going to use the electronic energy as a stand-in for the actual free energy. But for those of you familiar with quantum calculations, you know that we can actually we can get at this free energy here with Hessian calculations. So I won't really go into that. Okay, so hopefully now at this point, we're sort of, I'm sort of ready to show you what I find to be the big advantage of interacting with quantum codes using RDKit, right? So normally now you would have to go, you would open Gauss View or something similar, you draw the molecule, you will save the file, you'll run the calculations, you'll look up the numbers in the output file and go from there, right? So with RDKit, it's especially very easy to set up the calculation, right? So for example, if I just want my reference molecule to be ethylamine, right? I make my ethylamine, that's my reactant. That's my product. Let's make sure we did this right. So now I want to draw two molecules. Let's see, moles to grid image. That expects a list, so I'm going to put that in. And let's see how that looks. Yeah, okay. So that looks pretty good. I've made my molecule or my molecule sort of sketch, right? And now I just want to run this for the reactants and the products. Right, so I use my run XTB. For my reactant. And I want to optimize. This is pKa, so I want to do this in solution, in water. And my first molecule here, my reactant, has a charge. So I need to give it a charge here. And now I get my energy. Right, and then I do exactly the same for my product. So the hydrogen is lost. I think, hang on here, that has to be 2 dashes. That's my energy. And then I can calculate the difference, product minus reactant. And for those of you who are not quantum chemists, the typical units for a quantum energy is Hartree. And so you can convert that to kilocalories per mole with this constant or kilojoules per mole with this constant. I like to work in kilocalories per mole. I'm a little old-fashioned. So yeah, so let's see what we get here. So we have our delta E, our product energy, and our, oops, reactant energy. Yeah. And I can see I've made a mistake. Oh yeah. Yeah, so there you go. So here we have our relative energy, right? And so with just a few lines of code and some functions, some pre-written functions, right? You can trivially set up and generate coordinates by just typing in a few simple formulas, and you get you get the relative energies here.
Yeah. Good question. Could you comment on the accuracy of such an estimation?
How accurate is the difference? We'll get to that. That's why I picked the pKa's, because we have the experimental values here.
Okay, great.
So actually, what we'll do next is we'll calculate the pKa's of these relative to this and see how it does. So yeah. Oh yeah, one thing before I get there though. So let's look at this value here. Actually, it doesn't. It's a little bit different every time. Right. So here 115, 115, 116. Right. So that's already a kilocalorie per mole difference. And the reason for that is that we generate random coordinates. This function here has an embed, and it generates random coordinates. And so we actually already, for these simple molecules, we need to do a conformational search. And so let's see. So that, now I've actually forgotten in which, that must be here. Yes, so if you see here, by default, I set the conformational search to false. So, and I'll say a bit about what this does, but let's just make sure it works. So I can add the conformational search. This is, as you'll see, this is done with the molecular mechanics force field. And so, but if you run it now, you consistently get 116.29. Okay, so this is more about the precision, not the accuracy, but the precision is also important. Let me just show you what it does. So that is run XDB. If I ask it to do a conformational search, then it uses this get best structure, which is here. And so what you can see here is RTKit has the ability to generate several conformations. The default is 10, but you can change that. But in this particular implementation, it generates 10 conformations. It optimizes them using molecular mechanics, which means it also gets the molecular mechanics energies, and then it returns the structure with the lowest energy. If for your molecule you don't really trust the force field, right? You can, if you want to do your conformational search with your quantum program, let's say some DFT method, right? Then you can use this function here to generate your coordinates, and instead of optimizing them, you simply write out separate input files for each of these, run your quantum calculations, and then pick the structure with the lowest quantum mechanical energy. So that's entirely doable. But this is a way of doing conformer searches more or less, well, fully automatically using RTKit. So, but just for illustrative purposes, we're just going to use the molecular mechanics force field. Okay. So let's go back here. So that's the precision. The next thing is the accuracy, but I think we've been going at it for an hour, and I don't know if there's a way of polling people, but should we have a 5-minute break? I guess I'll leave it to my panelist. What do you think, Chris? Or
I think a couple of minutes break would be a good idea, just to let people catch up with the coding and things like that.
Yeah, that's also a good point. So let's should we just say 5 minutes?
5 minutes. So it's 5 minutes from now then. So okay.
Yeah. Super.
Yeah, it's interesting looking at the questions. So many of the questions you answer about 30 seconds after the question is posed.
Okay, that's good. That's
Yes,
excellent
really
news.
good. That's very impressive.
Well, yeah, I think it's because we have a lot of quantum chemists on board here, and so I went through the exact same process about I don't know, 3 or 4 years ago, where I sort of picked up on RDKit, right? So how do you there's this constant sort of or very common set of steps you do in a quantum calculation, right? So with a predefined order, and so it's basically just a matter of figuring out how to make RDKit do that. And in fact, it can do most of these things, and it actually does it quite well for organic molecules.
Yes.
Actually, I think I'll also take advantage of the break. So I'll be back in just 2 minutes.
Yeah, sure.
Okay, I'm back.
So, quick question for me. The XTP, what elements are covered?
I think it's all the elements up to 87, nuclear charge 87. So most of the periodic table.
Yeah, all the useful part anyway. So
All
organic
the
chemists.
yes, yeah, but also all the transition metals and
Yeah.
and that actually makes it sort of unique in the world of these semi-empirical methods, is that it actually performs quite well. It gives good structures and frequencies and things like that, also for organometallics, for example.
Yeah.
So in my experience, much better than, let's say, from MOPAC.
Okay, that's good.
Yeah, and I should also mention sort of that these are really Stefan Grimmer, who developed this. His intent was really to make a method that would provide good starting geometries for DFT calculations, or to calculate vibrational frequencies for large systems, or to do a conformational search. So in the parameterization of this method, it was never really parameterized against reaction energies. And so even though it wasn't, it actually does quite well, as we'll see, sort of depending on your definition of quite well, but yeah.
A couple of questions. At the moment, you're using a single node, I think. Is it possible to do this to run on a cluster?
Yes. So I mean, not on GoogleCoLab, but yeah, XTB is parallelized, so you can on. I don't think it's parallelized across nodes, but certainly within a node. I mean, with the shared memory set of cores, it's parallel.
Yeah.
But what I typically do, though, we use this for very high throughput, thousands of molecules, and so we actually give each CPU one molecule instead of, so we do it parallel in that sense.
Yeah. And a philosophical question, I guess, really. Why did you choose RDKit over other open source informatics libraries?
That is because I just from looking around, I found there was a lot of documentation. I see you posted the cookbook.
Yeah.
There's also the website sort of getting started in RDKit, which is really good and comprehensive. It has a very active mailing list, a very friendly mailing list where you can ask all sorts of questions. And they've also set up a Discord, which is sort of it's sort of a social platform, actually for gaming mostly, but they've set up a channel for RDKit where you can also get informal help. But it was basically, I chose it because there's a lot of help to be, a lot of help from the community and a lot of help that was easy to sort of find.
Yeah. Another question, does it scale to protein ligand systems?
So there are various flavors of XTB. And so what the default is the expensive flavor. So there are also cheaper, even cheaper methods that are capable of doing calculations on proteins. Now it's obviously slower than a force field, but there are also ways of using some kind of charge embedding. So I haven't really seen it implemented, but it wouldn't be very difficult, I think, to implement a QMMM type setup.
Yeah.
Yeah.
What kind of solvent models available?
Okay. So there are two. The one I'm using here is a generalized Born GBSA. And there's also, very recently, they added some type of Poisson-Boltzmann solvent model. So so these are the two continuum ones. I tried both for this example, and the accuracy is about the same, but I haven't done a comprehensive sort of comparison. And to my knowledge, neither solvent model implementation has been published. So there isn't really a paper I can point to.
There's a couple of questions about different applications. So things like, how is it, would it be able to install Jaguar or Gaussian, things like this?
On CoLab?
Yeah.
I assume. I haven't tried it. So basically
these of course
use,
are not open source, are they?
No. I mean, in principle, I mean, I would imagine, I mean, this is a Linux server. So in principle, one should be able to install anything here, but without actually having tried it, I'm a little hesitant to sort of advocate that. Now you only get two processors. So, I mean, but it is a free compute node. you only have it as long as the window is open and active. So I think after about 12 hours, they'll terminate your session. And that's also if you can sort of keep awake that long and constantly activate your browser. So it's not super for high performance computing. So it's you're sort of in the regime where, you know, if each quantum calculation takes a few minutes, right, then it might be worth doing on UsingGoogleCoLab.
Yeah.
But if there's something that you want to run overnight, then it's difficult to do on UsingGoogleCoLab because your session will sort of self-terminate when the window isn't active.
Here's an interesting one for you. Does Colab have compiler support, Fortran, C++, etc.?
I don't think so. I think you'd have to install it. Let's just try it.
Can you install gFortran?
You can, in principle, install anything.
Yeah.
I mean, like for example, I mean, you once you get Anaconda installed, then anything you can install with Conda, with pip, with apt-get, basically any. I mean, it's a regular Unix machine. I can try. I think. Let's see if
maybe we could leave that to the end and let you carry on.
Yeah. Okay. Yeah. Let's do that. Okay. So that's sort of the energy difference between these two. And now we want, if we go over here, let's say we want to make this, and now calculate how much the pKa has shifted. So that's right. That's fairly easy. We grab this. Actually, I'm going to skip ahead a little bit. So let's say we want to do all these. Right, so now we basically get to the optimization. Now we get sort of to where, in my opinion, RDKit really shines. So I want to do these 3, but you can imagine you want to do 100 or even 1,000 of these. So I'm going to define a list of amines files, and there are many repositories like Chembl or PubChem or things like that, where you can get the smile strings of 1,000 amines without too much trouble. But you can also write code to generate these. But let's say we just want a list of amines, and I'm just gonna define the neutral part, right? So here we have we put 1 fluorine on. 2 fluorines, and I'm going to copy this, 3 fluorines. And again, if you're not familiar with the syntax, you could draw these in ChemDraw or something like that. Okay, and so now we want to automate this process, right? So we have smiles, and we want to generate our mole objects. So we want to take the smiles here in our list. Right, so you can find fairly easily or generate a list of amines, but you're probably not going to find a list of amines with and without the proton. So this is what we're going to generate now. So we have the neutral form, and we're going to generate the proton or the protonated form. And so for this, we're going to use something called reaction smarts. So I'm going to define a reaction here. So I'm going to say I have a nitrogen, which I'm going to number. So nitrogen number 1. And I want to turn this into a protonated charged form. So that's my reaction. So the syntax here is a little special. I guess I'm not really going to go into it, but if you Google smarts or reaction smarts or things like that, then there are many examples and tutorials. Okay, but basically what this is going to do is this is going to turn all these into the protonated form. So we're going to have loop over our amines. And then we're going to generate the corresponding protonated form. And so for this, there's a helper function up here called oneReactions. So it's going to take our neutral amine as an input and the type of reaction we want to perform, which is a protonation, and it's going to generate the protonated form. And let's just convince ourselves that this works. So we'll convert it to smiles. Right, and you can see you get the protonated form here. Right, so this is really, in my opinion, where RT-Kit shines, right? So something that would be very, very tedious to do for hundreds of thousands of molecules, right? You can do in a few lines of code now with RT-Kit. Okay, so now we're gonna do exactly what we did before. We're gonna calculate the energy for this. So first we're gonna, okay, we can start with this. So we're gonna start with our protonated form. We're gonna do a conformational search, and we're gonna get the energy. And then we're gonna take the same thing here. Whoops. And for our deprotonated form, here we don't need the charge. And we got to get the energy. And then we're going to have our reaction energy. So that's the reaction energy for this system now. So we want the HA and the, our products are the HA ref and our deprotonated molecule. So and we're going to subtract our deprotonated reference plus this, and we're going to convert it to kilocalories. And to get the pKa, right, we're gonna convert this to a pKa change by dividing it by RT times natural log of 10, which in kilocalories per mole and 25 degrees Celsius, that's 1.36. So and then I happen to know that the pKa of our reference is 10.7. Well, I know that because Chris put that here on his website, 10.7. And I'm going to add my change in pKa to this. And then I'm going to append it to my list. Oh, I should make a list. pKa's. Oops. All right, and now we're going to run the calculations. Okay, And so here we are. So with one fluorine, actually, let's draw it. So draw moles to grid image like we used before. We're going to draw our means. And the legend, so on the writing underneath each molecule is going to be the pKa. That should work, I think. No, these are numbers and it wants a string. So and actually we're gonna round it up or round it down so it looks a little bit better. So we're gonna have 1 decimal place. Okay, the fun of live coding. Let's see. Oh yeah. Oh yeah, it still needs to be made a string. Let's see. New string. That's also not how you do it. There we go. Okay. So let's see. Yeah, so 7, 3, and minus 2.6. So 7 instead of 9, 3 instead of 7, and minus 2.6 instead of 5.7. So you can see so there's 2 ways of looking at it. At least in this particular case, as a pKa predictor, it's pretty much worthless. But what we're talking about here is an error in reaction energy of about 3 or 4 kilocalories per mole. So, you know, compared to experiment, there's actually a lot of DFT models that would struggle to get a similar kind of accuracy. Now, there are 2 issues here. One is the quantum method itself, and one is the solvation model. And so actually, I suspect here that the solvation, that most of the error here comes from the solvation model, and not from the actual quantum calculation itself. In fact, I have a link up here to a paper that I wrote together with Chris and Lars Olsen, where we use semi-empirical methods, not XTB, but semi-empirical methods like PM3 and PM6 using this approach. And we actually get pretty good pKa predictions. So yeah, but that's basically, that's what XTB and the GBSA solvation model is that's the kind of precision it's able to deliver here. So, but like I said, if you looked at some other reaction energy in water and you compare it to experiment and you got an error of 3 kilocalories per mole, you'd be pretty happy. It's just that pKas can be measured incredibly precise and need to be incredibly precise in order to be of any use. So, but obviously you can use this approach with any other quantum program. So what I want you to pay attention to here is more the automatization, right? That you can very easily generate the input, both reactants and products in a systematic way, and you can do it really fast. That's sort of the take-home message from this.
We have a quick question. Can you use constrain part of the molecule when you're doing the optimization?
Yes, so you can constrain either an internal coordinate like a bond length, angle or something like that. I do believe you can, I'm not 100% on this, but I do believe you can also constrain a particular Cartesian coordinate. I know for sure with the internal coordinates. I'm not so sure with the Cartesians. Yeah.
Another question.
Yeah, absolutely. Keep them coming.
Is it possible to generate conformers and then perform a conformational average?
Yes. Yeah. So in fact, here we're already generating 10 conformers. We're just using the one with the lowest molecular mechanics energy. But where are we here? Get best structure. RDKit can make as many conformations as you want. Here I ask for 10, but it can make any number of conformations. You can then subject each one of them, instead of just the one with the lowest energy, to a quantum optimization. You can take the energy and then conformationally average. Yeah.
Okay.
So yeah, also as I'll show, right, this syntax here is completely general. So you can basically perform any reaction you want. You can create products from any reactant. Any product from any reactant that can be done that in a reasonable sort of with any reasonable chemical mechanism. In fact, I'll show you that next. But if there are more questions, just let me know.
I think you're up to date now.
Okay. Okay. So yeah, so one thing you can do with quantum methods is relative energies. Another interesting thing you can do are barriers. Now, to estimate barriers. So to estimate barriers, you need to estimate a reaction path. And there are many ways of doing this. So in quantum programs, there are many kinds of interpolation methods. So Gaussian has QST2 and 3. So for example, QST2, you simply interpolate between the reactant and product coordinates and calculate, use that to sort of estimate the path, and then Gaussian can take this path and then try to find the transition state. There are also things like notch elastic bands, growing string methods, all these sort of things. One problem with those is that the atom ordering needs to be exactly the same for the reactants and the products. And so that can be excruciating to do by hand. And what I want to show you here are two different ways you can use some tools that we've written based on RDKit that can make this a lot easier. Now, so XTB itself has an interface to a growing string method, but it also has sort of an internal method that does sort of the same thing. So it's an interpolation method. So I'm just using this method as sort of a stand-in for any interpolation method. What I want to focus on is sort of the atom ordering and things like that. So there are two ways of doing it. So the first one here is reaction smarts. So we're going to make a reactant. So this is a molecule we've been working with in my group. So I just picked it. There's nothing really special about it other than that. So here's just how it looks. Okay, this is the molecule, and what we're going to do now is perform a reaction on this. So this is one where I'm gonna paste something in. I know that's a little bit cheating for people following along, but I'll do a lot of talking, so there'll be some time for you to type. So here I generated another reaction smarts, and I can actually show you what that looks like. Reaction from smarts, that's the one at the bottom. Okay, so what I do here is so I identify just the reacting atoms, right? So we're going to take this OH group that's going to add across this double bond, right? So to form basically a ring closure, as you'll see, and then make an OH group.
Could you paste the reaction smarts into the chat?
That is a great idea. I hadn't thought of that.
Yeah.
Let's see, like so. Do you see
Yeah.
that? Okay, and then you can share it with the
yeah. Okay.
Oh no, I can do that. No, I guess I cannot do that.
I can
But you
paste
can.
it to the entire audience. There you go.
Yeah, super. Thanks. That's a good idea. So that's the reaction. So if I apply this now to my product, well, I apply it to my reactant to make my product using a function that you have under functions here called run reactions. Oh, we've used that already for the pKa's. So then we make this product. Okay, let's see. Yes. Okay. So yeah, this is a little technical, but it's showing the hydrogen here. But that's sort of just that hydrogen is not really there, if that makes any sense. So the problem is I have to add hydrogens to this before I can perform this reaction because it involves a hydrogen. So like this. Okay, now you can see this looks different now, right? Before it was sort of red, it was implicitly part of this OH group, and now it's explicitly there. And it needs to be explicit because it's one of the atoms that are actually reacting. Okay, and so you can see it makes the reaction right by moving this hydrogen over on this oxygen and forming a bond here. Okay, now, so if you want to find the reaction path for this using an interpolation method, the atoms have to be in exactly the same order. And the problem is that they're not, they're shuffled, as I'll show you here. So if we label them, here, right, you can see it has sort of an arbitrary ordering. The ordering is defined, of the heavy atoms is defined in the smiles, but then it's sort of arbitrary how it adds the hydrogens. That's fine. I mean, an arbitrary ordering is fine as long as it's the same in the product. But as we'll see here, it's not. All right, so for example, this hydrogen here is number 12. Here it's number 1. But fortunately, there's sort of RDKit sort of keeps track of it, and so it's not really visible here, but RDKit does keep track of what atom is what from reactants to products. So I've written a little subroutine that reorders the atoms, and that you can use if you generate your products using reaction smarts. Okay, and so now you can see it's much better, right? So this atom here is transferred over to the oxygen. That's number 2, so 12 is bonded to 2, and atom 6 is bonded to atom 1, like it should be. And so this is so now in principle, this is ready for the interpolation. Of course, we have to work with 3D coordinates. So we need to make it 3D. And if we just embed, there's no need to embed the product if we've already embedded the reactant. So we simply embed the reaction here, the reactant, and I always, like I say, I always minimize it. Like this. Okay, so now it sort of generates an arbitrary conformation. And here I simply have to re-minimize the structure. I don't have to embed it again, it's already embedded. Well, we can see what happens if I don't minimize. Right, it simply introduces bonds, but it doesn't change the geometry at all. And so we can fix that. By minimizing it. So there's the, now that looks like a perfectly fine input structure. And notably, the atom ordering is exactly the same here and here. Okay, another thing that's important is that because we embedded first, the atom ordering here is a little bit arbitrary, right? And that's important because if you have labels on these atoms, then this is actually a chiral center. And so it's important that the pseudo-chirality is the same here and here, right? But by embedding first and then running the reaction, right, the coordinates here basically haven't changed, and so the pseudo-chirality is exactly the same. Okay, so let's try to let's just try to see what the barrier looks like here with the XTB. So to do that, I'm just going to follow an example they had. No, I actually have the link here in the notebook. Let's see. Yes, reaction path estimator. So here you can read more about the model. So it takes starting geometries, end point geometries, and then it needs some parameters that define this interpolation method. So we're actually gonna grab this while we're here. And add that. So that's our path input. Okay. So that's one thing we need, and we need to write that out. So that's one thing, and we also need to write out the geometries for the start and the finish. So let me write that out here. And I'll write the reactant. Oops. That's reactant done. products. And I think they wanted to call that. And I think you can call this anything you want. But my plan was just to grab the command from this example. So then it's a good thing I called the files the same thing. And that needs an exclamation mark to, whoops, to run as a batch. And let's see what we get. That's going to run a little bit longer, but not very much longer. So basically that's interpolating now between the reactants and products. And it does, I think I asked for 25 points. So it's going to save 25 points in between the reactants and products. And it finished. And I think somewhere it says that it saved the path. Yes, so the path is saved here in this file. So let's try to visualize that. And we want to animate it. And let's see what it does. Okay. Yeah, somewhere else in the file. Yeah, it's just XTB path. Okay, let's see. No. Okay.
I think you got a space after the XYZ, haven't you?
You have. We have. You're right. There you go. So that's the reaction path. And in that file, you also have the energies for each point. And I've made a little subroutine that just plots that. And there you go. So here's your reaction path. And you can see the barriers. The barrier's a bit high. This path will depend quite a bit on the starting geometries. And here I just sort of picked an arbitrary one. So it's quite possible that if you run this again, you'll see a different barrier. But the main point here is not really how XTB performs. The main point I wanted to show you here, there's actually two main points. Again, one, it's very easy to generate products from reactants. So it doesn't just have to be a simple protonation. It can be something actually quite complicated with this reactions files. And if you create your product in this way, then it's quite easy to, with this little subroutine here, to ensure that the atom ordering is the same. And that's actually the hard part in all of this. And then you can really give it to any reaction path finder that you use. It could be QST2 in Gaussian, or a notch elastic band, or a growing string method, or something like that. The final thing, so we're running out of time, so just very quick. So this works only if you generate your products from reactants using reactant smiles. But it would be nice, I think some people would like to simply be able to draw your reactants and your products, or take the reactant and the product from an XYZ file where it's not necessarily, where the atoms are not necessarily in the same order. And so for this, you can use another program called Atom Mapper. So this shows you the installation. And basically what this, here I'll just copy the code because we're running out of time. You clone it with RDKit. And so you can import it, you generate your products and reactants. So here, notice the difference now is I've generated both reactants and products, and the atom ordering is not the same here, certainly not for the hydrogens. But you can then use this atom mapper here to ensure that the atom ordering is the same between the two. So let's run that. And so what you see here is the reactant, and then it actually made 4 different products. And so the reason there's 4 is that your product is actually chiral, right? So if you look at these two here, the atom ordering is the same, but the chirality of this atom is different. The other thing is that there's actually 2 ways of making the product. There are 2 different reaction mechanisms that takes you from here to here, right? So the one we talked about previously, right, is the one where this hydrogen is transferred to the oxygen, and this oxygen makes a bond to this carbon, right? So you're breaking this bond essentially, but you could also break this bond. And that's the one actually here, right? So you're breaking this bond, so you're making a bond between this oxygen and this oxygen, and your OH groups comes from making a bond to this, from this oxygen to this carbon. And if the only information you have is the product and reactant structures, then there's actually no way to tell which is the preferred reaction mechanism. And so you actually have to run the interpolation from an example of each, from this one and from this one. Because if there's only one chiral center, then the reaction path, then the chirality doesn't really affect the reaction path energy. So, but yeah, bottom line is if you have a reactant and product structure where the atom ordering is completely arbitrary, there is a way to map that automatically using RDKit, while using a function that my group wrote that relies on RDKit. So that's, I think I have 5 minutes left, so this is probably a good time to stop and see if there are any sort of final questions.
Yeah, is it possible to obtain visualized localized molecular orbitals with XTB?
So it is, yes. Not in UsingGoogleCoLab, but XTB writes out a file that the program Molden can read. And so Molden you can use Molden to visualize the orbitals. And it can also localize the orbitals. There's a keyword in XTB for localizing the orbitals.
There's quite a few people complimenting you on the workshop. It was really great.
Oh, okay. Well, thank you very much. I'm happy to hear it.
Yeah.
Yeah. And so if you have any, I mean, so the notebook, everything I wrote now, right, is basically accessible to you. All the toolkits that are on GitHub are freely accessible. And so if there are any, people should feel free to contact me, or if it's an RDKit question, I really encourage you to use the RDKit mailing list, because there are a lot of experts on there that are actually better at RDKit than me. So, but if it's something, if there are questions particular to some of these subroutines that I wrote here, or the ones that we import from my GitHub repo, of course, I'm happy to. If there are any problems with that, I'm happy to help people out.
Yeah, I've put a couple of links to RDKit things in the chat, so super. People can use those.
Yeah, and reaction smarts, I see that. Yeah. So yeah, there is a learning curve to this, but it's well, if you are at all interested in automating the setup of quantum calculations, I really find that RDKit is it's a very, very powerful tool.
Yeah. I've been very impressed with Google Colabs and the way you used it. It looks to me like a perfect teaching tool as well.
It really is. So I teach a Python programming course for complete beginners, and also a machine learning course for complete beginners. And it's just, before we started using GoogleCoLab, we had all sorts of installation problems. I mean, you can imagine,
Yes, I know.
50 students with 50 different variants of the Windows operating system, and trying to get everything working on that was just a nightmare. And and this just solves all the problems. But it's not even, I mean, I use this even for research to prototype all my code. And once I'm happy with that, then I simply go up here and download a Python file to make a standalone sort of code that I then use on our servers.
Yeah.
But I find that Jupyter notebooks in general are just excellent for debugging, because you can run individual cells. You don't have to run the whole thing every time. Yeah. And it's very easy to visualize things as you go along.
Have you ever tried using this on a tablet?
It does not work on my iPad, unfortunately. I don't know why, but it does not work even with the Google native, I mean the Google browser.
Okay, that's a shame.
Yeah, but that's a shame, yeah. And I don't know why, because I don't think there's anything, fancy or anything like that. So I don't know what to say. Yeah.
There's a question here. Where can we find those courses that you give?
Well, actually, let's see. So the programming course, that's in Danish. All the material is in Danish, so I'm not sure. But the machine learning course is also an intro to Python at the same time. So and that one is available. I just have to find the link. So if you go to my my Twitter profile, and I can paste that in here. Then my pinned tweet. Well, I should just, instead of pasting this in, I should just paste in the link to the website.
Yeah.
So that's coming here. So it's called Machine Learning Basics. And so it takes you from very, very basic stuff. So it doesn't presuppose any Python at all. We start from linear regression with just absolute basic math. And we go all the way up to using a package called DeepChem, which is a machine learning model sort of specifically geared towards chemistry. And the course basically consists of a series of video lectures, all made with GoogleCoLab. It's in English, and I basically, every line of code is, you can watch me type out every line of code here. So, and you can follow along.
That sounds a fantastic resource.
Well, yeah, some people have been happy with it, and I should mention that there is one chapter is dealing with molecules, and that's basically an introduction to RDKit. So there's an intro here, and then there are some things. So I talk about smiles, I talk about smarts. I think actually there's a link to this particular video at the top of the notebook that we're working on. But then I also talk about fingerprints, which is something we do, or which is one way of generating input for machine learning models, the binary version of it.
Yeah.
So.
Okay.
Yeah. And so here I go a little bit slow just because it's there's no prerequisites for the course.
Yeah.
So, but with videos, it's easy to sort of skip through to the media part.
Well, once again, I'd like to thank you for giving this course. I'm sure if looking at the comments and questions, I mean, a lot of people have found this hugely informative and very much appreciative of the course that you've given. So thank you again. And
oh, you're welcome. I'm very happy to hear it.
A virtual round of applause for you.
Thank you.
Okay. So the next section of the Open Science Week starts in half an hour, and it's on the publishing side. Or anybody who's registered for that will have had a separate link for that. So I should be closing this down because I'm not sure the RSC can support more than one GoToMeeting.
It's having problems enough with one. So.
That's right, yes. Thank you very much, Jan, for all your forbearance at the start where we were sorting out all
no
the
problem.
glitches.
Yeah.
And
thanks everyone for your attention.
Right, thank you very much. Okay, I'll close it down now. Thank you.
Yeah.